Okay, today we'll have a look at lesson 2 of chapter 1, limits and continuity, part 1. So we'll spend 2 days on limits and continuity. Today we'll have a look at the first part of limits and continuity. So first of all, let's have a look at the learning goals. After this lesson, you are expected to first understand the definition of limits and one-sided limits of a function at a certain point, as well as their connections. Second, determine if the limit of a function exists at a certain point. Third, evaluate one-sided limits or the limit, if exists, of a function at a certain point graphically. Then understand the definition of continuity of a function at a point or on an open interval. Next, determine if the function is continuous at a certain point or on an open interval. Last, differentiate 3 types of discontinuities as a function at a certain point. Okay, first let's have a look at let's give it a quick recap of the instantaneous rate of change. So in our previous lesson, we have learned that the definition of instantaneous rate of change that relates to the limits, right? We use the limit to define the instantaneous rate of change. So specifically, if we are given a function f(x), is shown on the graph on the left, and 2 different points P and Q, coordinate B is x, fx. And the slope of the secant between P and Q is delta y over delta x, which is f(x plus h minus x) divided by the difference between x plus h and x, right? So this can be simplified to fx plus h minus fx over h. This is defined as the average rate of change between P and Q. Remember that? And h is not 0. Also note that when h, the difference between the x coordinates of the 2 points, when h is approaching 0, then the difference between delta y over delta x will approach the slope of the tangent line at P, which is also called instantaneous rate of change of fx at point P, or the derivative of fx at point P, right? So we denote the derivative or the instantaneous rate of change using the limit symbol here. So as you can see here, this is read as limit of fx plus h minus fx over h as h approaches 0. The limit of this function is defined as the instantaneous rate of change at our point P. Or this can also be denoted by fx prime or dy by dx. So this is the definition of instantaneous rate of change, or the derivative of fx at point P, right? So as you can see here, the derivative of fx at point P is defined using a limit. But so far, we haven't learned how to evaluate limit, right? So today, we're going to have a look at the definition of limit, the properties of limit, and some related concepts, okay? Okay, so first, let's have a look at the limit of a function at a certain point. Okay, I'll give you an example. The value of a function f approaches as its input x approaches some value is said to be the limit of f. So this is an intuitive definition of the limit. Limits are essential to the study of calculus, and as we will see, are used in defining continuity, derivatives, and integrals. Of course, we don't study integrals in this course. Okay, so let's consider this function here. Fx equals x squared minus 1 divided by x minus 1. Notice that x equals 1 does not belong to the domain of fx, right? Because the denominator is x plus x minus 1. So x equals 1 does not belong to the domain of fx. Regardless, we would like to know how fx behaves close to the point of x equals 1, right? Then we can start with a table of values as shown here. It appears that for values of fx, close to 1, we have that fx is close to 2, right? As you can see here, when x is 0.5, fx is 1.5. When x is 0.9, fx is 1.9. And when x approaches 1, such as when x equals 0.99, then fx approaches 1.99, right? This is a point to the left of x equals 1, but very close to x equals 1, right? And beyond that, if x equals 1.01, then fx equals 2.01. So as you can see here, when x approaches x equals 1 to the right, from the right side, fx also approaches 2, but from the right side, right? In fact, we can make the values of fx as close to 2 as we like by taking x sufficiently close to 1. We express this by saying the limit of the function fx as x approaches 1 is equal to 2. And therefore, we can use this notation here. Okay, be careful with this notation. Limit of fx as x approaches 1 equals 2. Okay, you should be able to know how to read this limit. Any questions? Okay, then let's give it a more formal definition of the limit. Well, actually, it's not very rigorous. The rigorous definition of the limit is not covered in this course. So we'll just give it an intuitive definition here. In general, we write the limit of fx when x approaches a equals L. If we can make the values of fx arbitrarily close to L by taking x to be sufficiently close to a on either side of a, but not equal to a. This is the definition of the limit of a function at a certain point, a. So note here, we read the expression, the limit of fx as x approaches a is equal to L. Okay, be careful with the reading of the expression of limit here. When evaluating a limit, you are essentially answering the following question. What number does the function approach when x gets closer and closer to a, but not equal to a, okay? Very close to a point a, but not equal to that point. The phrase, but not equal to a, in the definition of a limit means that when finding the limit of fx as x approaches a, we never actually consider x equals a. In fact, as we just saw in the example above, a may not even belong to the domain of fx. All that matters for limits is what happens to f close to a, but not necessarily what happens to f at a. You understand? So that's the intuitive meaning of the limit of a function at a certain point. Any questions? Okay, then let's have a look at the example here. So consider the following piecewise defined function. Fx equals x if x is smaller than or equal to 1. And fx equals x plus 1 if x is greater than 1. This is apparently a piecewise function, right? It has two pieces, depending on whether x is smaller than 1 or greater than 1. So observe from the graph that as x gets closer and closer to 1 from left side, that means from this side, when x gets closer to 1 from the left side, then fx approaches positive 1, right? Which is this point here. Similarly, when x gets closer and closer 1 to 1 from the right side, that means from this side, then fx approaches positive 2, which is here, right? We use the following notation to indicate this. Okay, so we write the limit of fx as x approaches to 1, x approaches 1 from the left side. From the left side, you should write it like this. X approaches 1 from left side. We simply put a negative symbol on top right of this number. You understand? So this limit equals 1. Okay, so how do you express the other side? We write the limit of fx as x approaches 1 from the right side. If you want to express from the right side, you should put a plus symbol on top right of this number here. So this limit, as we have just analyzed, equals 2. Understand? Okay. So this is called one-sided limit, either from the left side or from the right side. And the symbol when x approaches 1 from the left side here means that we only consider the values of x sufficiently close to 1, which are less than 1. Similarly, the symbol x approaches 1 from the right side, which is here, means that we only consider values of x sufficiently close to 1, which are greater than 1. So these two notations have different meanings, okay? One of them means when x approaches 1 from the left side. This means from the left side. From left side. And this notation here means x approaches 1 from the right side, okay? Do not confuse them. Any questions? Any questions? Okay. All right, so based on this, we have just talked about the left and right hand limit, right? Let's give it a more formal definition. Again, this is not a rigorous mathematical definition, but more intuitively usable definition. So in general, we write the limit of fx when x approaches a from the left side equals L. L is a number. If we can make the values of fx arbitrarily close to L by taking x to be sufficiently close to a and x less than a. So be careful with the statement here. Sufficiently close to a and x less than a. That's from the left side, right? This is called the left-hand limit of fx. as x approaches a. Similarly, we write the limit of fx when x approaches a from the right side equals L if we can make the values of fx arbitrarily close to L by taking x to be sufficiently close to a and x greater than a. This is called the right-hand limit of fx as x approaches a. Okay, so this is the definition of either left or right-hand limit. Again, this is just an intuitive definition. We won't talk about the more rigorous mathematical definition here, okay? This is not covered in this course, so probably you'll learn that in the university study. Okay, so actually, this is a precise definition of limits at a certain point. So usually we'll use mathematical language to describe sufficiently close. So how close is called sufficiently close? Usually we'll use a epsilon and a delta to define the sufficiently close. Okay, so this concept is only for reference only. Okay, if you are interested, you can check related materials after the class. This is not required for this course. Okay, and we're not gonna talk too much about this definition here. Only for your reference. Okay, so based on the definition of limits, left side limit and right side limit, let's have a look at example here. So given this function shown on this graph, can you determine the limits from this graph? A, the limit of fx when x approaches 4 from the left side. B, the limit of fx when x approaches 4 from the right side. C, the limit of fx when x approaches 4. D, f4. Okay, I'll give you 1 minute to think about this question. Okay, have we finished? We can directly observe the limits and the value of the function when x approaches 4 or at the point x equals 4, right? So if we if we go from the left side to x equals 4, when x approaches 4 from the left side, that's from this side, this function will approach -2, right? So therefore we say the limit of fx when x approaches 4 from the left side equals -2. And then if we approach this point from, if x approaches 4 to from the right side, this function will also approach -2 from the right side. Therefore, we say the limit of fx when x approaches 4 from the positive side equals -2, right? Because both of the left limit and right limit equals -2. We can say when x approaches 4, the limit of fx is -2. And then last is the image of 4, right? The image of 4 under f, which is also -4 or -2, right? Any questions? No? Okay, so you should be able to evaluate each of these. Okay? Make sure you understand the meaning of the limit and the image of a certain point. Okay, we can have a look at the solution here. I'll give you 1 minute to have a look at the solution here. Okay, this is a more detailed explanation of the solutions. All right, then next, because we just talked about the left-hand limit and right-hand limit, right? So now let's have a look at the connections between the limit and the left-hand and right-hand limit. So we have a theorem about the relationship between limit and left-hand and right-hand limits. So the connection between the limit and left-hand and right limits, left and right limits, is the limit of function fx when x approaches a equals L, if and only if the limit of fx when x approaches a from the left side equals L, and the limit of fx when x approaches a from the right side also equals L. So if and only if means the expression on the left side and the right side are equivalent. Okay. So from the left side, then we'll have the right side. And starting from the right side, you will get the statement on the left side. So that means if and only if. Or more precisely, we have the following equation. The limit of fx when x approaches a from the left side equals the limit of fx when x approaches a from the right side equals L. A consequence of this fact is that if the one-sided limits are different, then the two-sided limit, the limit of fx when x approaches a, does not exist, often denoted as DNE. DNE means do not exist or does not exist. Okay, any questions? This is a connection between the limit of a function at a certain point and the left-hand and right-hand limits of this function at a certain point. Okay. All right, so let's have a look at example here. Given the graph of a function here, can you determine each of the following for graph B? 1, the limit of gx when x approaches 2 from the negative side. 2, the limit of gx when x approaches 2 from the positive side. 3, the limit of gx when x approaches 2 for the image of 2 under the function g. Okay, I'll give you 2 minutes to have a look at this question here. Have you finished? Okay, let's see the solution of this question. First, when you approach 2 from the left side, that's from this side, right? And as you can see, the limit of gx when x approaches 2 from the left side, then the limit will be this one, 3, right? So the result of the first expression is 3. And when you approach 2 from the right side, that's from this side, then the limit of gx is this point here, which is 4, right? So as we can see here, when x approaches 2 from the left side or the right side, the limits of gx are different, right? The left limit of gx as x approaches 2 is 3. The right limit is 4. Therefore, right limit is not the same with left limit. Therefore, the limit of gx as x approaches 2 does not exist. So we put DNE here. This limit does not exist because the left limit does not equal the right limit. Okay, last one is the image of x equals 2 under the effect of function g. Apparently, you should find this from the graph. When x is 2, which is here, then gx is this value, which is 3, right? You understand? Any questions? Okay, so pretty straightforward, right? Okay, so next, similarly, we can also define the limits at infinity. For example, let's have a look at the definition of the limit at infinity. So these are just notations, nothing special, okay? So in general, we write the limit of function fx when x approaches positive infinity equals L. If fx can be made arbitrarily close to L by taking x large enough. If this limit exists, we say that the function f has the limit L as x increases without bounds. So for example, if we consider this function here, 1 over x squared. So we can easily draw the graph of this function, right? So this function will have a graph like this. This is y, this is x, y equals 1 over x squared, right? This is the graph of this function. You understand? So as you can see here, when x approaches positive infinity, this function approaches 0, right? So we use this symbol to denote this behavior. When x approaches positive infinity, fx, the limit of fx equals L. Apparently in this example, L is 0, right? Therefore, we say the limit of 1 over x squared when x approaches positive infinity is 0, which is denoted by this expression. Okay? Any questions? No? Okay. Similarly, we can also write the limit of fx when x approaches negative infinity equals m. If fx can be made arbitrarily close to m by taking x to be negative and sufficiently large in absolute value. If this limit exists, we say that function f has a limit L as x decreases without bound. So for example, we can consider the same function 1 over x squared. When x approaches negative infinity, that's from this side, right? It is obvious that the limit of 1 over x squared when x approaches negative infinity is 0, right? So we use a notation like this to denote this relationship, to denote this behavior. And also the precise definition is omitted here. We won't cover the precise, more rigorous definition in mathematical language. If you are interested, you can check the link here, okay? This is just a more intuitive way to understand the limit at infinity, okay? Any questions? So when you define limit, you should always consider the wording, sufficiently close enough, okay? Sufficiently close enough. How do you describe that behavior? Okay, similarly, we also have the definition of infinite limit. Again, this is not a rigorous way to define that. but a useful definition so far. Okay, so in general, we can also write the limit of fx when x approaches a equals positive infinity, like this, if we can make the value of fx arbitrarily large by taking x to be sufficiently close to a on either side of a, but not equal to a. Okay, for example, again, let's consider the same function, which is fx equals 1 over x squared. Again, the graph of this function will look like this, right? So we can denote the behavior of this function when x approaches 0. So here, we can say that the limit of this function when x approaches 0 is positive infinity, right? So we can use an expression like this to express this behavior. Also, similarly, we have the limit of fx when x approaches a can also be negative infinity. If we can make the value of x arbitrarily negatively large by taking x to be sufficiently close to a, but not equal to a. So for example, if we consider the function y equals -1 over x squared, so the graph of this function will look like this, right? You understand? This is a graph of y equals -1 over x squared. As we can see here, when x approaches 0, that's from this side or this side, right? When x approaches 0, the limit of this function is negative infinity. Imagine that when x is sufficiently close to 0 here, the value of this function will approach negative infinity. Therefore, we use this expression to denote a behavior like this. Okay. So if you want to evaluate the limit of this function, do not write DNE, okay? Do not write the DNE, but instead you could write positive infinity or negative infinity. You understand? Okay. All right, so we can take 10 minutes break, and after that, we'll have a look at the definition of continuity, okay? All right, let's take 10 minutes break first. Okay, next let's have a look at the concept of continuity. The graph shown here in figure A represents a continuous function. Geometrically, this is because there are no jumps in these graphs. That is, if you pick a point on the graph and approach it from the left and right, the values of this function approach the values of the function at that point. For example, you can see that this is not true for the function values near x equals 1 on the graph in figure 2, okay? Which is not continuous at that location. Okay, so this is an intuitive concept of the continuity of a function at a certain point, right? At x equals 1, left function is continuous. The right function here shown here is not continuous. Okay, so let's look at a more rigorous way to define the continuity of a function at a certain point. A function fx is continuous at a point x equals a if the following three conditions are satisfied. First, fx must be defined at x equals a. In other words, fa must be defined. Second, the limit of fx as x approaches a must also exist. Third, the limit of fx when x approaches a must equal fa. So all these three conditions must satisfy such that fx is continuous at a point x equals a. Okay? So graphically, you can think of a continuity as being able to draw your function without having to lift your pencil off the paper. If your pencil has to jump off the page to continue drawing the function, then the function is not continuous at that point. Okay, so next, let's have a look at a concrete example here. The following four graphs showing whether this function is continuous at a specific point x equals a. Okay, so first let's have a look at the first graph on the bottom left. On this graph, first of all, fa is defined, right? Next, limit of fx when x approaches a also defined. Third, the limit of fx when x approaches a equals fa, right? Therefore, we say that function fx is continuous at the point when x equals a. Understand? Okay, then let's have a look at the second graph here. First of all, if fa is not defined, the answer is not, right? So as you can see here, there is a hole on the curve of this function. That means fx is not defined when x equals a, which also means fa is not defined, right? Therefore, we say fx is not continuous at x equals a because the first condition fails to hold. Then let's have a look at the third graph here. Is first of all, if fx is defined at x equals a, the answer is yes. Fa is defined. Okay, then let's consider the second condition. If limit of fx exists, The answer is not, because the left limit and right limit at this point are not equal, right? If they are not equal, the limit of this function at this point does not exist. Therefore, the second condition cannot be true. Therefore, fx is not continuous at this point, right? Okay, then let's consider the last graph here. Can the three conditions be met? The answer is no. Okay, first of all, fa is defined. Second, limit of fx is also defined, right? Because when x approaches this point from both left and right, the limit of fx is this point, right? However, the third condition does not meet, because the limit of fx when x approaches a is here. However, the value of fx when x equals a is here. These two values are not equal. Therefore, we say this function is not continuous at x equals a. You understand? Okay, so be careful here. We are only talking about the continuity of a function at a certain point so far, okay? Okay, next let's have a look at the continuity of a function on an open interval. Okay, there is a definition of the continuity on an open interval. A function f is continuous on an open interval a and b if it is continuous at every point in this interval. Furthermore, a function is everywhere continuous if it is continuous on the entire real number line from negative infinity to positive infinity. Okay, so this is a concept of the continuity of function on an open interval. Okay. All right, then let's have a look at a concrete example to illustrate the concept of continuity. Okay, let's consider this function shown on this graph. We can draw this function without lifting our pencil, except at the points x equals -5, x equals -2, x equals -1, and x equals 4, right? Thus, intuitively, fx is continuous at every real number except at these four numbers. At x equals 5, x equals -2, oh sorry, x equals -5, x equals -2, x equals -1, and x equals 4, the function fx is called discontinuous. Okay, so let's have a look at the difference between these discontinuities. First, at x equals -2, we have a removable discontinuity because we can simply remove the discontinuity by redefining f -2 to be 3.5, right? You understand? Formally, we say fx has removable discontinuity at x equals a if the limit of fx when x approaches a exists, but is not equal to fa. Then this discontinuity is removable. Note that we do not require FA to be defined in this case. That is, A need not belong to the domain of Fx, right? On the other hand, at x equals -5 and x equals -1, we have jump discontinuous because the function jumps from one value to another. From the right of x equals 4, we have infinite discontinuity because the function goes off to infinity. These types of discontinuities are summarized below. So note here, we have 3 types of discontinuities, okay? So you need to differentiate the 3 types of discontinuities: removable, jump, or infinite, okay? So let's make a summary below. So these are the 3 types of discontinuities of a function at a given point. So in the first case, in the first graph, if the limit of fx does not equal fa, then this is called removable discontinuity, which is illustrated in this graph. Okay. Why is called removable? Because you can simply remove the discontinuity by letting fa equal that limit. Okay, the second type of discontinuity is called jump discontinuity, which is illustrated in the graph in the middle. So in this case, the limit of fx when x approaches a from the left side or from the right side does not equal, right? If it's not equal, then the limit of this function does not exist. Then we say this is a jump discontinuity. And the third type of discontinuity is called infinite discontinuity, which is illustrated in the third graph here. So as you can see here, either the limit of fx when x approaches a from positive side equals positive or negative infinity, or the limit of fx when x approaches a from the negative side equals positive or negative infinity. Therefore, in this case, we say this function has infinite discontinuity at the specific point x equals a. Understand? Okay, so we have just learned the concept of continuity at a certain point, continuity and in an open interval, and 3 types of discontinuities at a specific point, right? So based on this knowledge we have just learned, let's see an example here. So examine the graph shown here and answer the following questions. First, state the domain of this function. Second, evaluate each of the following expressions. Third, is this function continuous or discontinuous at x equals 1? If applicable, state the type of discontinuity. Okay, I'll give you 5 minutes to have a look at this question here. Okay, have we finished? All right, let's see the solutions of these questions. First, the function is defined for all values of x. So the domain for x is all real numbers, right? Because the expression of that function is given to you, as you can see here. If x is less than 1, then fx equals 0.5 times x squared. If x equals 1, then fx equals -2. And if x is greater than 1, fx equals negative x plus 3. That covers the whole number axis, right? So the domain for x is all real numbers, or x belongs to the real number set. Second, the graph of this function to the right of 1 is represented by a straight line that approaches y equals 2. So from this graph, we can evaluate the limit of fx when x approaches 1 from positive side. Okay, do not forget the small plus symbol on top right. Okay, equals 2. Then if you trace along the graph from the left, you approach 0.5. So the limit of fx when x approaches 1 from negative side equals 0.5. Since the left-hand limit and right-hand limit are not equal, we say the limit of fx when x approaches 1 does not exist, right? Left limit, right limit does not equal. Therefore, the limit of fx at this point, x equals 1, does not exist. Okay, question D. From this graph, we can easily evaluate that the solid dot at 1, -2 indicates that f1 equals -2, right? That means the image of 1 is -2 under function f. Okay, question 3. At x equals 1, the one-sided limits exist, but are not equal. The function has a break or is discontinuous. At x equals 1, the y values of the graph jump from 0.5 to 2 at x equals 1, right? Therefore, this type of discontinuity is called a jump discontinuity. Understand? Any questions? Okay. All right, then let's consider another practice. Examine the given graph and answer the following questions. Again, first, state the domain of this function. The expression of that function is given to you. Fx equals the ratio between x plus 1 and x minus 4. Second question, evaluate each of the following expressions. First, limit of this function as x approaches 4 from the positive side. B from the negative side. C the limit of this function as x approaches 4. D f4, image of 4. Then last question is this function continuous or discontinuous at x equals 4? State the type of discontinuity if applicable. Okay, again, I'll give you 5 minutes to think about this question by yourself. Okay, have you finished? Okay, let's have a look at the solution together. Question 1, the function y equals x plus 1 over x minus 4 is not defined when the denominator is 0, right? Which occurs when x equals 4. Therefore, the domain of this function is x belongs to the real number set, but x cannot be 4. Okay, another way to state the domain is from negative infinity to 4, union with 4 to positive infinity, exclusive. Okay, you can use either notation. Both of them are acceptable. Okay, question 2. Tracing along the curve from the right towards x equals 4. The y values increase without bound. There is a vertical asymptote at x equals 4, right? So we have learned how to draw the graph of this function in MHF4U, right? In our previous course. There is a vertical asymptote at x equals 4. The right-hand limit does not exist. We use the symbol positive infinity to express the behavior of this curve. So we say the limit of this function as x approaches 4 from positive side equals positive infinity. So again, do not just write do not exist. You need to write the behavior of this function. So a more accurate way to express this is to use positive infinity symbol here, okay? Do not just write DNE. Okay, next, the curve is traced from the left towards x equals 4. Then the y values decrease without bound. The left-hand limit does not exist. But we know that when x approaches 4 from the left side, this function will approach negative infinity. Therefore, we use this symbol to denote the behavior of this function when it approaches this point from the left side of 4. Okay? Negative infinity. Okay. Therefore, we say the limit of this function from left side and from right side are not equal, right? Because one of them is positive infinity, the other one is negative infinity. Therefore, using the results from part A and B, we say the limit of this function when x approaches 4 does not exist. Okay, that's why it does not exist. Question D, since the function is undefined when x equals 4, we say f4, the image of 4, does not exist, right? Because simply it's not defined there. Okay, question 3. This function is undefined at x equals 4. Since y values either increase or decrease without bound as x approaches 4, then this function is said to have infinite discontinuity at x equals 4. You understand? Okay, then let's have a look at another practice. This is the last question of this lesson. Okay, I'll give you 5 minutes to have a look at this question here. Okay, have you finished? Yes, let's have a look at the solution here. Okay, this function, okay, note here the expression of this function is given to you, right? Which is 2x squared over x squared plus 1. Apparently, the function is defined for all values of x. There's no limitations for our independent variable x. So the domain of this function is x belongs to the real number set. Okay, second, evaluate each of the following expressions. Tracing the graph of this function from the left of 0, we can see that the limit of this function as x approaches 0 from the left side equals 0, right? Trace the graph from the right of 0. We can see the limit of this function as x approaches 0 from the right side equals 0. Therefore, from parts A and B, we can see that the left hand and right hand limits at x0 equal to be 0, right? Therefore, the limit exists for this function when x approaches 0. This limit is also 0, right? Remember that we say the limit of this function exists if and only if the left limit and the right limit of this function exists at a certain point, right? And also, if all the limits exist, their values should also be the same. D, the point 0, 0 is on the graph, right? Therefore, f0 equals 0. Okay, question 3, the function is continuous for all values of x, since there are no breaks in this graph. Understand? Okay, any questions here? No? Okay, so let's make a summary of today's lesson. Let's revisit the learning goals for today. So after this lesson, now you should be able to understand the definition of a limit and one-sided limits of a function at a certain point, as well as their connections. So be careful with the definitions of the limit and one-side limits, okay? Second, determine if the limit of a function exists at a certain point. The limit of a function exists at a certain point if and only if the left side and right side limits exist, right? Third, evaluate one-sided limits or the limit if exists of a function at a certain point graphically. Next, understand the definition of continuity of a function at a point on an open interval. So if we check whether this function is continuous at a certain point, you need to check 3 things, right? The value of that function at that point, the limit of that function at that point, and then if the limit of that function equals the image of that function at that point, right? Then determine if a function is continuous at a certain point or on an open interval. Last, differentiate 3 types of discontinuities of a function at a certain point. Remember, there are 3 types of discontinuities, which are removable discontinuity, jump discontinuity, and infinite discontinuity. Okay? So this is end of lesson 2 of chapter 3.